Welcome to this explainer. Today we're diving into the absolute unsung hero of the whole artificial intelligence revolution. We're talking about data preprocessing. When we hear about machine learning, we immediately picture the glamorous stuff, right? Self-driving cars, predictive text, medical breakthroughs. But honestly, absolutely none of that happens without a highly structured, rigorous assembly line working behind the scenes. Think of data preprocessing as the crucial manufacturing pipeline that actually makes machine learning possible. We have to take all these messy raw materials from the real world and refine them way before an algorithm can even start to learn. So that brings us to a pretty fundamental question. What actually happens when you feed an algorithm absolute garbage? Well, the reality is the real world just doesn't neatly organize itself into perfect spreadsheets for us. Real-world data is notoriously messy, it's unstructured, and it's absolutely full of errors. If you just take that raw information and dump it directly into a machine learning model, the algorithm is either going to draw some wildly inaccurate conclusions, or it's just going to crash and fail entirely. It's that golden rule of computer science: garbage in, garbage out. Okay, so let's dive into this by walking down our data pipeline step by step. We're hitting 5 key stages today: reading and understanding data, handling missing values, encoding categorical variables, normalizing data for fairness, and finally splitting for the final test. Right, let's kick things off with stage 1, reading and understanding data. This is basically the loading dock of our factory. Most raw data rolls up to the loading dock in formats like CSV or TSV files. Using a super powerful Python library called Pandas, we import all of this into a data frame. Now, if you're picturing a traditional spreadsheet or a SQL table, you've hit the nail on the head. Every single row in this grid represents a distinct observation or a sample. And every single column, that represents a specific variable, which in the machine learning world we call a feature. This simple two-dimensional grid is literally the foundation for everything we're about to do. But here's the catch. Once the data is in there, we can't just stare manually at a table with millions of rows. It's impossible. So to really get a grip on what we're working with, we use a few essential diagnostic tools in Pandas. We use head just to pull up a quick snapshot of the first few rows. We check the shape to find out exactly how massive this data set is. We run columns to get a nice clean list of all our feature names. And crucially, we run isNull to instantly flag our immediate problems, specifically figuring out exactly which columns are missing information. Which leads us perfectly into stage 2, handling missing values, or as you'll often see it in the code, dealing with NaN. Because as soon as we run those diagnostic checks, we inevitably find holes in our data. Missing values are usually represented in Python as NaN, meaning not a number. And here is why this is absolutely critical. Machine learning algorithms are basically just incredibly complex calculators. They're built entirely on math. If you try to feed a blank space or a text string like NaN into a mathematical equation, the calculation just shatters. The model simply cannot process it. We have to clean this up before moving forward. So how do we actually fix a missing value? Well, we've got a few options. The most aggressive move is to just drop all records containing missing values entirely, using something like drop_NA. But if you're working with a small data set, throwing out an entire row of valuable data just because one single feature is missing, that's going to severely hurt your model. Instead, we can be a bit more surgical. We might drop records only if they're missing data in a highly critical column, or, and this is often the smartest approach, we replace the missing data. We call this imputation. If the missing data is a category, like a missing city name, we just plug in the mode, the most frequent category. If it's a number, we can replace the blank with the mean or average of that specific column. It keeps our data set robust without sacrificing precious rows. Okay, our missing data is patched up. Next up is stage 3, encoding categorical variables. This is our translation phase. Remember earlier when I said algorithms only speak numbers? They have absolutely no idea what string text like gender or city means. We have to translate these categories into math. Now, we have 2 main ways to pull this off. The first is label encoding. It's simple. It assigns a unique incrementing integer to each category. So category A is 0, category B is 1, category C is 2. Easy, right? Well, actually, this creates a really dangerous trap. The algorithm might look at that and incorrectly assume that because 2 is a bigger number than 1, category C is mathematically greater or more important than category B. To avoid that false numeric weight entirely, we usually prefer one-hot encoding. This turns categories into distinct binary vectors made entirely of zeros and ones. So how does one-hot encoding actually work in practice? It's kind of like flipping switches. First, each possible category gets a unique integer value. Then, we build a binary vector with a specific position for each of those integers. To translate a category, we just flip a single switch to 1 in the spot that corresponds to that category, and we leave every other spot as a 0. Finally, we swap out the original text in our data frame with this brand new binary vector.
The result is brilliantly clean. Category A simply becomes 100, Category B becomes 010, and Category C becomes 001. They are now completely distinct mathematical entities. The algorithm can effortlessly crunch these binary vectors without ever assuming that Category C is structurally larger than Category A. It's a flawless translation from text straight into math.
That brings us to stage 4, normalizing data for fairness. Basically, this is where we level the playing field.
Think about this. What happens if you're analyzing a dataset about real estate, where one feature is the square footage, which is measured in the thousands, and another feature is the number of bedrooms, which is usually a single digit? Many machine learning algorithms rely heavily on measuring the geometric distance between data points. If we don't scale our features, those massive numbers from the square footage are going to completely overpower the tiny numbers from the bedroom count. They'll dominate the learning process unfairly. Normalization steps in to scale all these features down to a standard playing field. To get there, we use a couple of specific mathematical transformations. Now, you definitely don't need to memorize the exact math right now, but these two formulas, z-score and min-max scaling, they are the true engines of normalization. They grab our wildly varying data points, whether they're in the millions or tiny decimals, and they shrink them down into a uniform, comparable scale. Usually that means cramming everything between 0 and 1 or centering it perfectly around 0. Once we run our data through those scaling formulas, the payoff is huge. First off, it dramatically enhances overall model accuracy. Like we just talked about, it stops the large scales from unfairly hogging the algorithm's attention. But on a technical level, it also promotes incredible stability during the optimization process. It literally stops the math from exploding, ensuring our model achieves much faster convergence while it trains. And honestly, when all your features share the exact same scale, the relationships between them are just so much easier to interpret, both for the algorithm and for us humans. All right, we made it to the end of the pre-processing pipeline. Stage 5, splitting for the final test. It is time for the ultimate exam. I want you to think of your machine learning algorithm like a student cramming for a massive final exam. To do this right, we have to split our beautifully prepared dataset into 2 distinct chunks. We take the lion's share of the data, usually around 80%, and designate it as the trained subset. That's the textbook our student uses to study and discover patterns. But we absolutely must lock away that remaining smaller portion, the test subset, entirely out of sight. That locked away data acts as the unseen final exam. Why go through all this trouble? Simple. Splitting prevents cheating. Think about it. If we didn't split the data and we just trained and tested the model on the exact same full dataset, the algorithm would basically just memorize the answer key. It would look like an absolute genius in the lab. But the second you deployed it into the real world to face brand new, unseen information, it would completely fall apart. By keeping a separate test set, we guarantee the model is evaluated on its actual ability to generalize to new data, not just its ability to memorize the past. As we wrap up this explainer, if there's one thing I want you to take away, it's this. Machine learning isn't magic. It's completely dependent on meticulous, rigorous preparation. An algorithm is only ever going to be as smart as the data it's trained on. We've walked through exactly how to clean, translate, and scale our inputs today, but I want to leave you with a thought. Even after your data survives this entire rigorous pipeline, what happens when the real world suddenly shifts, introducing entirely new patterns that your pristine model has literally never seen before? How do you prepare for that? Keep that in the back of your mind the next time you're staring down a raw data set. Thanks so much for joining me today, and keep questioning the data.